From the Weather Channel, a special presentation. What can giant sequoias in California, living today, tell us about the weather of the Middle Ages? How do scientists in Tibet know which way the wind blew thousands of years ago? What caused the most fearsome creatures ever to walk the planet to become extinct? And could it happen to man? Join us as we uncover clues to the climate puzzle. Over time, man has devised numerous and ever more complex ways to chronicle the patterns of nature all around him. But weather and climate were measured and recorded long before man's arrival. Not measured by human hands, not written in any known language, but recorded just the same, as surely and accurately as if man himself were there. Recorded in the earth, stored in a million places, in 1,000 different ways, waiting to be brought together like pieces to a puzzle. It's a puzzle that, when solved, may tell us about the climate of the future. But to unlock its secrets, we must first uncover clues from the past. Around the world, a coalition of climatologists, meteorologists, geologists, paleontologists, and more are uncovering new and remarkable information every day. Studying tree rings from the Sierra Nevada, ice from the glaciers of Tibet, rock samples from the mountainous south of Mexico, deep-sea sediment from the Pacific Basin, even cores of solid stone from an amazing formation in the Newark Basin of New Jersey are yielding new pieces of the puzzle. And as the clues accumulate, we learn what the climate was like not just hundreds or even thousands of years ago. We learn what the climate was like millions of years ago. How warm was it when dinosaurs ruled the earth, and how do we know? Did a change in climate make it possible for man's earliest ancestors to finally flourish? Can man adapt to climate change as some creatures have adapted in the past? Or could we fail, as some perhaps have failed in the past? When life first appeared more than 3 billion years ago, Earth was a much warmer place, even at the poles, and our world's climate has been in constant flux ever since. When the dinosaurs arrived 250 million years ago, Earth was slightly warmer than today. But it grew warmer still. With Earth at its warmest, the end of the Cretaceous period, 65 million years ago, saw the extinction of the dinosaurs and the appearance of man's earliest ancestors, probably much like the modern-day lemur. A series of ice ages began about 2 million years ago. Glaciers grew to cover much of the planet. After millions of years of evolution, modern man made his appearance about 350,000 years ago. This pattern of glacial advance and retreat continues today. We're currently between glaciations, unless man himself has altered the equation. High in the Sierra Nevada range of California are found some of the oldest living things on the planet. The bristlecone pines, and these giant sequoias live to be thousands of years old. Dendroclimatologists take core samples of the trees, drilling in and removing a cylinder of wood about as thick as a pencil. The process does no harm to the tree. By studying its rings, how much it has grown each year of its life, scientists are uncovering secrets of Earth's recent past climate, if you call the last few thousand years recent.
In essence, you can think of the trees as kind of being like little thermometers and rain gauges scattered across the landscape if you know where to look. When we look at the rings, we see a lot of variability from year to year in the widths of the rings. Here's a period, starts at 1100, the trees growing from left to right across the screen, and it was a period of very warm temperatures. These growth rates are equivalent to those that we've seen during the 20th century. This period is often referred to as the medieval warm period.
It was during this time the Vikings are known to have sailed the previously icebound North Sea for Iceland, Greenland, and the New World.
In this next sequence of rings, in the 1600s, tree growth is slower This was a time when temperatures were colder, glaciers moved down their valleys, crops failed in Western Europe. Sometimes this is referred to as the Little Ice Age.
The Little Ice Age continued through the middle of the 19th century. The image of a snow-covered London, seldom seen today, appears often in the works of Charles Dickens.
The night was bitter cold. The snow lay on the ground, frozen into a hard, thick crust, so that only the heaps that had drifted...
And while even the oldest trees live no more than several thousand years, scientists have discovered a way to take their studies back well beyond the earliest days of living specimens. Here's how it works. When studying a living tree, researchers simply count the rings to move back through time, each ring representing 1 year. While rings from different trees never match perfectly, the pattern of ring widths alternating between wide and narrow is identifiable. Finding a series of rings that match that pattern, say from a tree that is preserved or fossilized, allows scientists to, in effect, overlap the two sets of rings and thereby date the fossilized tree as well, and the count backward in time can continue. In this way, even trees that have been dead for hundreds or thousands of years, if preserved properly, can tell us about the climate of the world in which they lived. What's learned here is confirmed at other sites around the world by studying another part of the tree, its pollen. Owen Davis of the University of Arizona, Tucson, and Dorothy Petit of Columbia University's Lamont Doherty Earth Observatory in New York both search for what is to them hidden treasure, pollen, the almost indestructible remnants of plants long gone. The pollen is gathered by drilling into lake beds and bogs, where sediment, anoxic or oxygen-free, has preserved the pollen.
There are two reasons for using pollen. First, they're really resistant to decay. The other reason is that the plants produce them in huge quantities. You know, like a giant cottonwood tree like this will produce tens of millions of pollen grains every year. There are a lot of them, and so since there are a lot of them, they're spread around the environment by the wind, they give you a good statistical representation of what the plants are near the area.
Dorothy Petit explains how the samples are processed in the lab.
We use screens, and then we use acids, sulfuric and hydrochloric acid, to dissolve the sand and silt. We get rid of the clays, and what's left are just pollen, if we can, pure pollen. What we're primarily interested in are pollen and macrofossils that'll tell us more about species changes.
Because one of the causes of species change is climate change. Each species of tree has a preferred climate. We can tell what the climate was like by studying what the vegetation was like. Pollen samples vividly illustrate how much North America has warmed since the last ice age. Northern pines in Florida, 18,000 years ago, a common sight. Today we call them northern pines for a reason. Spruce, too, have retreated to colder climes, while warmer temperatures have allowed oak to advance significantly from their Gulf Coast habitat of 18,000 years ago. We think of weather and climate as atmospheric phenomena, but one of the places climate variation is recorded most accurately is in the sea, and one of the ways it's recorded is with oxygen isotopes. Isotopes are different forms of the same element. All oxygen atoms, for example, have 8 protons. Most have 8 neutrons, too, for a total mass of 16. But some oxygen atoms have 10 neutrons, for a total mass of 18. So we speak of oxygen 16 isotopes and oxygen 18 isotopes. In fact, scientists know that exactly 0.2% of all oxygen atoms are O18 atoms. Water molecules with O16 atoms are lighter than water molecules with O18 atoms, so these water molecules evaporate faster. The end result, water vapor with lots of O16 and liquid water with lots of O18. When water vapor turns to rain, it all gets mixed up again. But when it turns to snow, say when an ice cap or glacier is forming, the O16 gets locked away. It doesn't mix back in with the O18-rich water that remains. The colder the planet gets, the more O16 is locked away as ice, and more O18 there is in the oceans. Knowing that allows scientists to do an amazing thing. From deep beneath the ocean floor, they can retrieve the fossilized shells of creatures that lived in the oceans thousands, even millions of years ago. Measure the amount of O18 in those shells and tell us how much of the planet's water was locked away as ice, and thus how cold it was when that creature died. Columbia University's Lamont Doherty Earth Observatory boasts the largest collection of deep-sea sediment cores in the world. Samples representing all the world's oceans and 160 million years of Earth's climatic history are logged, labeled, stored, and studied. They provide an invaluable source for learning what Earth's climate was like in the distant past. Other life forms store oxygen isotopes just as effectively. Coral grows in layers much like tree rings, each layer faithfully recording the temperature of the water in which it grew. And researchers at the University of Michigan have discovered tiny calcium carbonate stones called otoliths in the ears of fish do the same, record the temperature of the water where the fish swam, even if it swam its last stroke millions of years ago. Oxygen isotope readings can be taken anywhere water is found. In fact, some of our most detailed climatic information comes from ice cores taken from glaciers and ice packs, such as this one in Tibet.
Much like tree rings, there's annual layers in the ice cores, and you can count back several thousand years. The deepest ice cores now go back about 200,000 years.
Ice core samples provide an invaluable piece of the climate puzzle. Bubbles of ancient air revealing the actual mixture of atmospheric gases, their isotopic chemistry, and more. Ice cores can even reveal past wind direction to those who study the thin layers of atmospheric dust encased in the ice.
Each region tends to have its own array or characteristic chemistry of fine particles. We can try to fingerprint where the dust is coming from.
And thus know which way the wind blew thousands of years before Windsox, Weatherman, or Bob Dylan. Glaciers could once be found here in America as well.
For the last 2 million years, approximately, it's about 1.8 million years, there have been at least 4 really major glaciations and corresponding interglacials.
In South Dakota, an amazing discovery is giving researchers new insights into Ice Age America and bringing the distant past to life for scientists and tourists alike.
Our best age on this, and it's a composite of 6 dates, is that we're right at 26,000 years ago. This would be the last part of the Ice Age.
In a sinkhole near Hot Springs, the bones of dozens of elephant-like mammoths, a species extinct now for some 11,000 years, have been exquisitely preserved. And the excavation of the site is allowing researchers to recreate the environment of the time.
The pollen tells us that we had essentially no trees, that it was a cold grassland, a steppe of grassland, if you want to use that terminology. Maybe some stunted trees like you'd find in the Arctic tundra right now along little water courses, but not the pine forests you see today. We're thinking that we had a cold, a sort of a paraglacial region within 150 miles of the ice front.
This and other sites have yielded important links in the puzzle. Dr. Agenbrod was the first in the U.S. to discover preserved mammoth dung. That may not at first seem like something to celebrate, but it's a vitally important find, allowing us to study the climate of the time by studying the plants these massive creatures ate.
We can look at the plant communities and get the time, and we can begin putting together a paleoclimatic model. We can get the temperature tolerances of plants, we can get the moisture tolerances, so we get temperature and moisture data, and we can do this through slices of time.
Just a few hundred miles away, but millions of years distant, the fossil record provides a fascinating dichotomy. For if you go back further in time, you find that where mammoths would later roam an Ice Age frozen landscape, once there grew palm trees.
What we have here is a fossil palm leaf. It's actually an imprint of the leaf in sandstone. Here we have a palm in southern Colorado which gets regular, very cold freezing in the winter, and we also have fossil palms as far north as southern Canada in the late Cretaceous. The world we live in today is refrigerated compared to what it was 65 to 45 million years ago.
Indeed, a review of just a few of the fossils found in Colorado, Wyoming, and other northern states show all the characteristics of tropical flora.
Leaves tell us a lot about the climate in which their plants are growing. And if you go to a tropical rainforest, what you'll find are very large leaves, they have smooth margins, and very elongate tips. And that's because the plants that are growing in tropical rainforests are under no or very little stress in terms of temperature or lack of moisture.
So not only is the type of plant revealing, the very size and shape of fossil leaves offers valuable clues to the climate puzzle. While tree rings, lake sediment, and ice cores can take us back in time on the order of thousands, even hundreds of thousands of years, in New Jersey, a project is underway that is already providing insight into the climate of the past 200 million years. In the process of sedimentation, sand, silt, and organic matter are deposited layer after layer and harden into rock over millions of years. In the Newark Basin, geologic forces have acted to lift and expose those ancient deposits, allowing researchers to sample millions of years' worth of sediment without drilling millions of dollars worth of holes. The cores are 15 feet each foot representing 20,000 years of sedimentation. Scientists are able to, in effect, read the cores by studying the color of the rock.
The colors is a primary way for us to deduce what the climate history was at the time. They alternate between dark gray to black layers, and those intervals represent when the lake was deep. Those alternate with red sediments where the lake was dry and these sediments were exposed to air, were essentially oxidized.
As the drilling progresses, a pattern begins to emerge. Cycles, regularly alternating patterns of gray and red, representing alternating episodes of lake bed and desert.
The small scale cycle, those about approximately 10 feet, we believe correspond to about 20,000 years. The next higher one, about 50 feet, is 100,000 years, and then the multiple of 4 of those is 400,000 years. And finally, the longest cycle, 2 million years, would then be a multiple of 5 times the 200 or 1,000 feet.
Arduous labor and astute detective work combine to show scientists climatic rhythms on a timescale never before known. But across the continent and around the world, scientists are working on solving what may be the greatest climatological puzzle of all.
This white layer marks the boundary between the Cretaceous and the Tertiary periods. It's the level that marks the extinction of the dinosaurs. Below this level, in older rocks, are dinosaur fossils. Above this level, there are no dinosaurs.
The KT boundary, a layer of rock, ash, and rare metals laid down 65 million years ago. It could solve a puzzle that has baffled scientists for decades. Did the cataclysmic impact of a comet or meteor cause a sudden shift in Earth's climate and the extinction of the dinosaurs? The pieces of the puzzle come together. From Colorado.
This layer contains a variety of indicators that this layer was deposited by fallout from an asteroid. It contains a super high abundance of iridium, which is a platinum group metal that is rare on the surface of the Earth, but is very common in asteroids and meteorites.
From Haiti.
We find grains of shock quartz in these deposits, which represent the shock-deformed portion of the Earth's crust, which was then distributed as a fine dust through the Earth's atmosphere. We also find tektites, which represent the portion of the Earth's crust that was melted and then ejected out of the crater.
From around the world.
This boundary has been found in over 150 localities in all ocean basins in Europe, North America, New Zealand, Asia. It's global.
We traveled to the south of Mexico with Doctors David Kring and William Boynton. For years, scientists have theorized about a massive collision between Earth and a comet or meteor. Boynton and Kring and others have suggested the extinction of the dinosaurs may have been caused by just such an impact. That theory, though still theory, may soon be confirmed at the Chicxulub crater site in Mexico's Yucatan Peninsula. Boynton and Kring have come to Chiapas to sample rocks blown here from the crater hundreds of miles north, each stone perhaps bearing part of our answer. For as with any good puzzle, the whole picture will be formed by putting together the pieces.
About 65 million years ago,
65 million years ago, some distance north of here,
a large asteroid or comet, about 10 kilometers in size.
And we're talking a meteor that's probably, or an asteroid that's probably 12 miles in diameter,
collided with the Earth.
there was a giant impact of a comet or an asteroid.
Traveling at approximately 20 kilometers per second, and it's a very large rock going very fast.
Our best analogy to such events are nuclear bomb tests on the surface of the Earth.
As it hits the Earth, it vaporizes. It melts what it hits and causes a tremendous crater to form.
This excavated a huge crater. It moved material around to a depth of 35 to 40 kilometers. And for a moment, there was a hole in the Earth's crust 14 to 15 kilometers deep.
And within minutes, or seconds to minutes after the impact, the Earth rebounds and sprays the vaporized meteorite, the dust from the target rock, the molten area in the center of the crater, right back out that hole into the atmosphere and into the upper stratosphere.
If we were to take all of this dirt and stack it up on a football field, it would have reached from here to the moon 24 times. It's a lot of material.
In addition, there is evidence that there were wildfires produced by the impact event. These wildfires would have produced soot, like any fire does, and the soot would have risen into the Earth's atmosphere and, again, could have blocked sunlight from reaching the surface of the Earth.
Dust, which is blown out of the crater, then forms a veil around the Earth in the outer stratosphere, blocking solar light from getting down to the surface of the Earth and turning the lights off on the planet.
What's more, much of the rock vaporized at Chicxulub was limestone, which contains abundant carbon dioxide. After the initial cooling, the subsequent greenhouse warming may have lasted thousands of years. No matter how the data is interpreted, the results of such an impact would have been catastrophic.
What you find is that below the boundary, we have a fairly diverse flora that's composed of conifers and ferns and broadleafed evergreen trees. At this level, 30% of those plants disappear. We lost all of the dinosaurs with the exception of the birds, and we lost a great number of terrestrial plants. We lost all the marine reptiles, all the flying reptiles, and a great deal of the marine phytoplankton. This is one of the largest extinctions of all time.
Man perceives his Earth as immutable. We seem unable to grasp how a world that has been just as it is today all through recorded history could change so drastically, so unexpectedly. Could the sort of extreme climatological shift that occurred in the past happen again today? Today, the Philippines' Mount Pinatubo still smolders from its 1991 eruption. The dust and ash it ejected into Earth's atmosphere, visible in yellow in these satellite photographs, has lowered temperatures globally 1 full degree, according to the National Oceanic and Atmospheric Administration. With the spring of 1993, the world emerged from one of the coldest winters on record. Perhaps we've had just a taste of the events of 65 million years ago. Could it happen today? Research continues in an attempt to understand the delicate interaction between Earth's atmosphere and the life it supports, in an effort to solve Earth's climate puzzle. Many clues remain to be discovered, yet as the pieces of the puzzle come together, they begin to form a picture of a world far more fragile, far more mercurial than we ever realized.